So I've never been recorded before. Can you hear me okay? All right, very good. So maybe not why you should switch to DB2, but why you should expand your skills. So I'm going to talk about the new features of DB2 9.7. We'll be sure to finish by 20 till, and I want you to feel free to speak up during the presentation and ask questions. If we're running slow, then I'll cut the questions off. But I really don't have any set number of charts that we have to go through. I've sent you a lot of charts that you can review at your leisure, and we'll just try to hit some of these highlights as we can. First, I'd like to get, what we're going to cover is first, Oracle application migration made easy, then autonomics in DB2, then compression, data partitioning, and then there's a whole lot of backup material that you can go through at your leisure. Professor Ledeen has the link. Now, I'd like to get a feel from all of you. How many of you know something about database? Okay, most. Okay, how many know Oracle? Okay, a few. And how many know DB2? 0. Okay, this is your lucky day. Because a problem that people have had in the past when they wanted to move from Oracle to DB2 was that the migration wasn't very easy. But with this new version of DB2, it's all done for you, almost all done for you. So those of you who know a little bit about Oracle can see all these things are now handled in DB2 9.7 with no change. Oracle SQL, PL SQL, concurrency control, and all the rest of it, and SQL plus scripts. They'll now run on DB2 without alteration, and I'm going to show you how they do that. By the way, those of you who know a bit about database but don't know Oracle, what are you running on? MySQL? Okay. Okay. You know there's or you probably don't know, there's a free downloadable version of DB2. It's called DB2-Express, DB2 Express-C. Freely downloadable. So you might want to get that and play around with it. Okay. Compatibility features. This is the good thing about, one of the many good things about DB2 9.7, compatibility features. There's a registry variable, the registry is where DB2 keeps its parameters, called DB2 compatibility vector. You set that to ORA for Oracle, and this is what happens. You've got SQL PL, which is DB2's query language, stored procedure language, and you've got PL SQL, which is Oracle's query language. They both go into DB2. They've got a DB2 compiler. We've got a PL SQL compiler. The same plan, that's the access method, is generated, and it all runs in the DB2 engine. So that's what happens when you set that vector. And this will be meaningful to those of you who do know Oracle a little bit. All these things are now handled for you in DB2. These are many, many Oracle capabilities which you can now run through DB2. No change. And this is not emulation. This is the engine where this is running. And you may know Oracle SQL Plus. DB2 has a CLP Plus, which is just about identical to that. Now, that's all I'm going to say about that, but there's a lot of backup material in the back. Okay, autonomics. I'm guessing that this cartoon was probably created before any of you were born. If I remember correctly, this appeared in the New Yorker. The gist of this is that people would like for computers to fix itself, to fix themselves. And that is kind of what DB2 does, and I'm going to tell you some ways in which it does that. First of all, there's a configuration advisor. When you install DB2, there are a lot of parameters that you can tune. Here's a listing of them online, but maybe you don't know what those parameters should be. Maybe you don't have the faintest idea what they should be. you can run a configuration advisor, and the configuration advisor will ask you a few questions like, is this an OLTP workload? Is this a business intelligence workload? And will configure the system for you. And then it will print out something here and show you what it did. For example, the buffer pool. Buffer pools are where your database memory is. So that's about your most important memory heap. The buffer pool size, it was 250 by default. When you installed DB2, you had 250 pages, 4K byte pages. Now look what the configuration advisor has done with that. It's decided you need 35K buff pages. So a big difference. And it's changed a lot of these other parameters also. So you wind up, after installing DB2 and running the configuration parameter, configuration advisor, with a fairly well-tuned database without doing a darn thing. Now there's also something called the design advisor. Let's say you have your database up and running. You've created a database. It's running. You're wondering if you should maybe create some indexes because things seem to be running a real long time. Or you're maybe thinking you should change your database design a bit. The design advisor, you can put one SQL statement in as an input parameter. You can put a whole workload in, or you can tell DB2 to go to the place where plans are stored. The plan is the access path into the database. It's a memory heap called package cache where the DB2 plans are stored. And you can tell DB2 to go to the package cache and run every plan that's sitting in there waiting to be executed or sitting in there from having been executed. And the design advisor will figure out what indexes you should create and other kinds of tables you should create. And it will spit out a nice little bunch of recommendations in data definition language, which then you can turn around and run. You can tell it to run it, or you can tell it to wait till later. Here's a typical run that was actually done. On the left here, you have your workload execution time. If you have 100% execution time base load, you spit out, DB2 Design Advisor spits out DDL, data definition language, that it recommends that you run based on the workload that you gave it, and you come up with a new design. And now, instead of 100% execution time, you're down to about 15%. So that's a typical thing that you can do. So you've got your database set up, you've got it working efficiently. You'd like to be able to monitor it. Businesses use this a lot. It's called a health monitor. And it will tell you when there's some problem in your database or there's an approaching problem in your database. For example, those of you who have created databases know that one of the things that may happen is you may define a table space, the physical storage for that database, and you may define it as 100 megabytes, and you may run out of space. You maybe didn't define it big enough. Maybe it's 500 megabytes. This health monitor will tell you when that's about to happen. And it'll send a note it'll send a note to a pager, it'll put it in a log, it'll email you, whatever you want to do. And you can even put a little script in there that says, don't notify me, just make it bigger and use the space over here, for example. So there are many, many, many things that you can monitor and head off at the pass, so to speak, so that you really don't have these unfortunate problems that just crop up in the middle of when you're trying to run your production workload. Now, this is something that I really love. Automatic object maintenance. There's a configuration parameter in DB2 called automate on, automate, and you can set it on or off. I always set it on. Then you can do many, many things. Most of you, I imagine, know that a database has to be backed up from time to time, so that if you have a problem, you can restore back to an earlier period in time or back to the current period in time. You've got to decide when to take those backups. But if you want, you can write a script, put it in DB2, and DB2 will take the backup for you whenever you said to. The same with run stats, which is the way DB2 figures out how to the access path into the database. It does an access of the database, the tables, the indexes, and it figures out what's going to be the best access path to get to that data. Should I use an index? Should I scan? What should I do? Many other things. You can have run stats run whenever it needs to be run. So guess what? You don't need to worry about your tables getting out of whack anymore because of old statistics. So that's all available to be done through the automatic object maintenance capabilities. Now, I want to take a checkpoint. Tell me if I'm going, I'd like for you to say if I'm going too slow, too fast, or just about right. So first, let's see hands for people who think I'm going too slowly. Nobody. First, let's see hands of people who think I'm going too fast. Nobody. Oh, 1, 2, okay. So can I assume that everybody else thinks it's just about right? Okay, well, I'll try to slow down a little bit. And if you don't see, if it seems like I'm going a little too fast, just say that again, please. And I'll do that and maybe elaborate on it a little better. Automatic storage management. This is another one of my favorite things. Those of you who have worked with a database know that you have to say, when you create a table, what table space you're going to put it into, and then you have to say where that table space physically resides on storage, right? Okay, you can now get around all of that by declaring automatic storage management and pointing DB2 to a set of devices. So DB2 will then place your data on those devices, and you don't fool with it anymore, and you don't worry about running out of space until you fill up all those devices. Here's how it works. Your statement is create database name, automatic storage, yes, on, these are file systems. In this case, it's data storage path 1 and data storage path 2. So you create the database on those paths, and DB2 creates containers, which are the physical files, inside data storage 1 and data storage path 1, data storage path 2. Data storage path 1 and data storage path 2 are Unix designations. If it were Windows, you might do C:, D:, E:, F:, G:, etc. Here are your storage devices, and each one of those DB2 will create containers in there. And then when you create your table space, you say create table space TS1 managed by automatic storage. That means anytime you put data into table space 1, it's going to go on these 5 devices. 5 in this example. It can be 8, 16. And what DB2 will do as you create that, as you add data to that table space, is it will stripe the data in a round-robin fashion on these containers. So the first block will go here, the next block will go here, the next block will go here, here, here. Then you start over again. The 6th block will go here. So it's evenly striped, it's randomly distributed, and performance is the best. This is what we used to have to do manually, but now we can do that not manually. We can also, if we like, specify an initial size for that table space. We want it to start out here at 500 bytes. An increased size, each time it's increased automatically by DB2, how much do we want it increased by? And here we're saying 100 bytes. And we can specify if we want to a max size. We don't want this table space ever to get any bigger. Yeah?
Are you striping in different drives?
Yep, you sure are. These are drives.
Okay.
Yeah, so block, 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 or actually extent is the terminology. Extent, 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 extent. Then you stripe back on the first drive. So like if it was C, D, E, F, G, it would be C, D, E, F, G, and you would rotate between the drives. And that's all done automatically for you. Okay, one nice thing about 9.7 is that you can now alter databases to take advantage of automatic storage, even if they weren't created that way. Didn't used to be, but as you can see, it's very simple to do that. You've got a database, you say alter, add storage on, and you list your storage path names. Those are those names that we saw a little earlier, either EFG or the Unix file system names. Now that you've got the database configured for automatic storage, you go down here to your table space. I should maybe just do a quick little drawing. Thank you. Just for those people who are not familiar with this, with terminology. Here is your machine, okay? Here is a database inside, I'm sorry, here is an instance of DB2. That's an instance of the code. And inside that instance, you can have a database. This is logical. This is not physical. You don't physically have an instance. Well, you do physically have an instance because you install the code. But I'm talking logical. So you have a database in an instance, and then inside that database, you have table spaces. And inside a table space is actually the physical or it points to the physical representation, which is a container, and another container, and another container. These are disks. Okay. Inside that table space is your table. Okay, so that's just to make sure we're all on the same wavelength. Okay, so you've created your database, you've altered your database to take advantage of automatic storage. Then you alter your table space, which was pointing to one drive here, maybe it was pointing there. So now it's altering it to still point there, but also to take advantage of this new storage that you just said you were going to have. Now, if you want to, if you say, I want this just to be on the new storage, I don't want it to be on that old storage, you just get rid of that original connection, and DB2 will put all the data that was here into here and into here, again using the striping mechanism. And the only thing that you did to make that happen is you said alter table space name, rebalance. That means rebalance from the old container to the new ones that are automatic storage containers. Okay, that's all I'm going to say about that, unless there are some questions about automatic storage. Yeah?
So, if you call rebalance, it doesn't use the old storage?
Doesn't use it anymore. It will use it if you don't say rebalance. It'll use the old and the new, actually. And you can't touch the old storage anymore. It's out of your hands. You can't alter it. You can't do anything with it. DB2 takes it over.
So when it uses the new storage, does it only stripe on the new storage and doesn't do anything with the old storage?
That's correct. All the new rows will go on the new storage, but of course you have old rows on the old storage, so it'll work with those. It'll update those. It'll delete those, whatever you ask. But it won't put anything there anymore. It'll put everything on the new storage. Any other questions on automatic storage? Okay. Now, STMM, Self-Tuning Memory Manager. This is another great thing. Excuse me. This works on basically your biggest DB2 memory heaps. What are those memory heaps? There are buffer pools, one or many. These are where your data rows come in and go out. I think you know that DB2 will read rows and write rows. and work on the rows that it has read and then write them out? Well, the place it does that is the buffer pools. Those are memory heaps. You can make them big, you can make them small, you can individualize them for particular workloads. There's a lot of art that goes into designing your buffer pools. Another big memory heap is the sort heap. That's where DB2, if you say select ABC ordered by X, that ordered by statement is probably going to do a sort. This is the memory where it does that sort. Your lock list is, if you go get a row, you put a lock on that row so that other people won't try to update that row. That's how you maintain your integrity. So the lock list keeps track of all of that, which rows are being updated, which rows are just held in a select but still held. Okay, the package cache, remember I said a little earlier that DB2 figures out an access path into the database, which it hopes will be the most efficient access path. All databases do this. And that access path is made into what's called a plan, and the plan goes into what's called a package cache, because package is another name for the access path, and the total database memory. So what the self-tuning memory manager does is it looks at all those memory heaps and it balances among them. If it looks like you need a lot of sort heap and buffer pool A is not doing much, it'll grab memory from buffer pool A. So now your buffer pool heap, maybe it was 10 gigabytes, now maybe it's 8 gigabytes. Okay? It'll also, let's say all your buffer pools are busy, all your sort heap is busy. You really need more memory everywhere in all these heaps, your lock list, your package cache. DB2 will go and get memory from the operating system, if it can. And you've specified a high limit as to how much you'll let it have of the operating system memory. For a standalone system, that's recommended at 75 to 90% for a standalone system. And the nice thing about this is no DBA intervention. It's doing it all for you under the covers, and you don't have to fool with it. So here's how you turn it on, and it's on by default, as the chart says. Update database config, that's where a lot of your configuration parameters live. For database name, using self-tuning memory on. Okay, so now you've got it on. So then you just set each parameter to automatic. DB2 set update database config for database using lock list, automatic. Using sort heap, automatic, etc. And for buffer pools, the syntax is a little bit different. You do an alter buffer pool name size automatic. So that's how you turn it on. And so I want to talk to you about when you should use this. Well, I use it all the time. But it's particularly good. If you have a lot of buffer pools, it's real hard for you as the DBA to tune those buffer pools. So this can really help. It's going to sample from 2 to 120 times per minute and take action. So that's a lot faster than you could do it. So it's real good for multiple buffer pools. It's good for a memory varied workload. If you have a lot of queries coming into your database and you don't really know when somebody's going to jump on and run the big business intelligence query that just hogs all the memory and all the other resources, or you don't know when he'll go to lunch and you won't need all that memory, it's really good for a memory varied workload, or a workload where you don't know what your memory requirements are. A lot of people will turn it on initially and get it tuned the way they think works pretty well, and then they'll turn it off. Okay, now I'm going to show you a real interesting experiment that they ran. So they had 10 agents, in other words, 10 users, executing queries with the order by clause. So what does the order by clause do? That makes you put the data rows that you've selected into a certain order. Well, how do you do that? You're probably going to have to sort. So you're probably going to have to write to that sort heap we talked about a little earlier, which is a memory heap. Okay, so they had these 10 queries executing together, and they execute along, and after several iterations, some of the indexes are dropped deliberately. So then all of a sudden you start sorting. So your sort heap needs to be a lot bigger. So your workload's going to slow way down. So this is an actual experiment that was run. So here's your 10 queries over here. These are different intervals. You can see they're all doing about 1,000 seconds per iteration. So they're running. You see they're staying right about the same. They're pretty well tuned. All of a sudden you get over here, drop the indexes. What happens? All of a sudden DB2 needs a ton of memory for the sort heap, and it doesn't have it. So the sort heap is too constricted. It's too small. When your sort heap is too small, the sort spills over to disk. Well, what do we know about disk? Good class, an order of magnitude slower. So here's what happens to your execution time. You go from 1,000 seconds to over 6,000 seconds. So the STMM kicks in. This is all automatic. Says, oh my goodness. It goes and gets some memory for sort heap. And look, in the very next iteration, you're already down to 3,000. Next iteration, you go down a little lower, and it kind of evens out here. Now, you're never going to have the good execution times that you had when you were using that index, before you dropped the index. But the point is that your execution time became much, much better, even in just the next iteration. Okay? So here's some more actual tests that were run. Here's DB2 just installed, absolutely no tuning. The configuration advisor wasn't run. The design advisor wasn't run. Nothing was run. Right out of the box, you're getting about 1,800 transactions per minute. Now, here is the DB2 experts who run benchmarks for IBM. They were able to get 6,300 transactions per minute after they carefully tuned the system, which is what these guys do for a living. Now look over here. Here's STMM. It was able to get the same amount. So that would make you feel pretty small if you had been doing performance tuning for a living, as I have. So it's really good stuff. So, and it makes your life much easier. And then you have to go and find another job to do, like migrate people from Oracle to DB2. I'm telling the truth, and so now I have to learn C for some partner who has some really old code, and I don't know C, so this is an interesting assignment. Okay, the importance of compression, saving storage. Oh, I'm sorry, I've finished with STMM unless there are questions about STMM. Okay, I'm going to talk to you about compression. By compression, I mean making the rows smaller. Saving storage is very good because storage, as you guys probably know, is your most expensive component. And as you all know, it's slower. And also compression, to our surprise, when they started this, they thought it was going to save a lot of disk space and that would be good. What they found was that it actually, by improving the I/O efficiencies, because you can have fewer rows, fewer pages coming in because the rows on the pages are smaller, so you get more rows on the page, and so fewer I/O operations are needed. And that actually can speed up queries. And I'm going to show you that in a minute. Okay, here's how the compression works. DB2 has, I'm not kidding, the best compression in the business. So here's some rows. Here's a row that has data Fred, 500, 1,000, Plano, Texas, 24385. Here's the second row. John, 500, 20,000, Plano, Texas, 24385. Okay, what DB2 does is it builds a dictionary over here, a little dictionary that it sticks right in the table space. And this, don't forget, this is table-wide, all over every row in that table, not just in the page. Okay, so it takes Fred. It sees that 500 appears here and in here. So in the dictionary, it inserts pointer 01. This is actually all binary. And the value, 500. And then back into the row, it plugs 01. Okay? And we keep going. Now, here's another pattern that repeats. Plano, Texas, 24385. These are 3 columns in the row. So, entry 02 in the dictionary is Plano, Texas, 24385. In the rows, it comes back over here and inserts a 02 instead of Plano, Texas, 24385. It goes on to the next row. So you can see you could save an awful lot of space, and that is exactly what happens. Any questions about that? So you've got the dictionary right in the table space with the rest of your table, which is now much smaller. Okay, the data is compressed everywhere. On the disk, your tables and indexes are compressed. Here's your buffer pool, the memory area where you're working with your rows that you've read in and are writing out. It's compressed there. It doesn't get uncompressed until an agent, we call it an agent, a DB2 agent, pulls that row out to work on it. And then it's uncompressed and compressed back and put back into the buffer pool. So as you can see, your buffer pool is going to have room for a lot more rows because they're little rows now. They're not so big as they used to be. Even your log buffer, your log is where you write after commits, you write your an image of the page so that you can recover. Your log buffer and your log disk are compressed. So it's compressed everywhere. Again, it's real easy to put it on. Create table, my table, compress yes. Or you can alter table, my table, compress yes. And the creation of the dictionary is all done for you. It wasn't in DB2.9, but DB2.9.5 and DB2.9.7, the dictionary is automatically created when you load your data. So here's my table. And in this example, you've got an existing table with uncompressed data, and you're going to reorg it, which means write all the rows out and read them all back in so they'll be neat and in sequence. And you come up with compressed data and a dictionary. But what you could do, let's say this is just a flat file, okay? And you're running the load utility, or you're running an insert statement to get the data into the table space. So you've got all this uncompressed data in this flat file. You run load or insert, and you get automatically compressed rows and your little dictionary. By the way, the dictionary is about 100 megabytes. It's incredibly small because it's all in binary. Okay, here's some sample performance queries. We ran 22 queries on a CPU-bound system. Now don't forget, it takes CPU to compress and uncompress those rows. Nothing's free. So our total time here, down at the bottom here, was 4194 with no compression. With compression, it was 4331. So it's a little worse. The percentage difference is 103. But you got a 60% compression ratio. That means you were using 60% of the space you were using before you compressed. So you might say, okay, even if I'm running at 103% of the CPU that I was using, that's okay because I got this great disk savings. But now let's look and see what happens on an I/O-bound system. This time, you've got your 22 queries. With no compression, they used 2258.2. I imagine that's kbytes. I mean, either megabytes, probably gigabytes. And they compressed it down to 1597. So that's a 71% savings in this I/O-bound system. So that's a tremendous space savings. And there was actually, not only did your CPU not run longer, but it was a 29% performance improvement because, as I say, a query could get more rows with one grab, and so your CPU was actually faster. It was a good deal. Okay, here's a little chart showing you some compression statistics. This is the total storage, about 65,000 kbytes, so that's 65 gigabytes in version 9.5. Version 9.5 with compression brought that down to about 45,000. And then version 9 with a capability we call lob inlining, where large objects, lobs, are stored in the table with the data instead of in a separate area. And then finally, version 9.7 with lob inlining and compression, we're down now to about 15,000 kbytes from 65,000. So I think that's all, and we're just about to run out of time, so I'm not going to cover partitioning. If there are any questions about compression, otherwise I'll say a few words about partitioning, or if there are any questions really about any of this. Okay, so I will cover partitioning real quickly. DB2 has three kinds of compression. There's the database partitioning feature, and I'm going to talk, the three kinds are listed over here, and I'm going to talk to them in more detail in a second. Table partitioning, which is also called range partitioning with index partitioning, and multidimensional clustering. So let's see what these are. DPF, or data partitioning facility, is database partitioning. So you've got a database that is on two machines. This is a machine, this is a machine. Your data is split between these two machines through hashing. See, each machine has its own disk. And each machine has its own CPU and its own memory. This is called a massively parallel processor, or massively parallel processing. Okay, and you can have hundreds. We show 2 here in the example. And that is a very efficient way of spreading your data out so that each machine is working on a lot less data. So that's database partitioning. Here is multidimensional clustering, and I'm glad I got to cover this because it is actually a really neat thing. It's a cube. Over here, you've got 3 dimensions here, as you can see. One dimension is nation. In our example, we have Mexico and Canada. Another dimension is item. So we've got little widgets and big widgets. And a third dimension is year. In our example, 1997, 1998. Okay? So the data is stored with multidimensional clustering in blocks. So one of these little blue things is a block. And all of this little cell right here is called a cell. So if you wanted, for example, to get all the rows for Canada and big widgets in 1997, you would be picking this cell right here with these blocks in it. As you can see, that's a very, very fast way to access the data, because you're getting all the rows, and your indexes, as you can see, are tiny. It's just 1 to point to right there. This is the final. Oh, should I? Well, I guess we've got 3 minutes, huh? This is the final kind of partitioning. Here's a table called sales data. Here's that table partitioned into 3 partitions. And this kind of partitioning is nearly always done by month. It's just what it seems to be most useful for. So now it's still one table. The applications see one table. But the table is physically partitioned over 3 table spaces, a part in table space A, a part in table space B, and a part in table space C. So that is table partitioning. And for my last chart, I'm going to show you a horrendous chart where it shows you can actually use them all together. This is database partitioning, the blue things on the top. Then you take one of these partitions, and it's actually split up by alphabetical order. So you've got table partitioning going on here. A table's partitioned into 4 partitions on this particular database partition. And then on this particular table partition, you have your multidimensional clustering cubes that I was talking about here. So you can really have a lot of fun with database design. And that is it, unless somebody has a 1-minute question. Okay, that's it. Thank you very much for your attention. And look through your backup material. In particular, look for the DB2 Info Center and go to Developer Works because you can get so much free stuff there. Sample code. If you want to write a Perl program that does X, it's really good.